In this next section, we're going to look at roots of quadratic equations. So we're going to start off by looking at this theorem. And this theorem says that if we've got a quadratic az squared plus bz plus c equals 0, a quadratic equation, if we know that z equals x plus iy is a solution, then we know that we have another solution, which is the complex conjugate of z. So we know that x minus iy must also be a solution. I'm not going to prove that in this video, but I'm going to do that in another video because it's not on the specification, so you can watch that if you're interested. So for example, if we had a quadratic equation here with the solution z equals 9 minus I, then we know that it's going to have another solution, which is the complex conjugate of z, which is 9 plus I. And if you wanted to, you could check that if you substitute in 9 plus I, you do get 0. And you might want to do that now, just to make sure that that does actually work. If you substitute in z equals 9 plus I, you will get 0. Now this theorem here has this condition that a, b and c have to be real numbers. This condition here just ensures that it works. It won't work if either a, b or c are non-real numbers or complex numbers. Well, this theorem is actually normally stated in terms of roots of quadratics. So for real numbers a, b and c, if the roots of the quadratic equation, given here, are non-real complex numbers, then they occur as a conjugate pair. So what that means is that if we've got a quadratic, if we know one of the roots is non-real, then we know the other root is its complex conjugate. So for example, here we've got a quadratic function, and we know that one of the roots is 5 minus 6i. Well, straight away, without doing anything, because the coefficients 1, minus 10 and 61 are all real numbers, then we can apply the theorem and we know that another root is going to be 5 plus 6i. So now we're in a position where we can look at all the different possible cases for the roots of a quadratic. The top two cases you've met before. So for this quadratic, this is an example where you've got two distinct real roots. The next quadratic is an example where you've got a repeated real root. And the next two examples are examples where you've got non-real roots. So if we know that 2 plus 3i is a root of this quadratic to the left, then we know straight away, because 1, minus 4 and 13, the coefficients are real numbers, then we know that the complex conjugate, 2 minus 3i, is also going to be a root. Similarly, because 1 and 4 are real numbers, the coefficients in the quadratic, we know that the complex conjugate of this root, which is minus 2i, is also going to be a root. And we say that these are examples of quadratics where the solution is a conjugate pair. Conjugate pair meaning just that one is the complex conjugate of the other. A consequence of this is that it's impossible for a quadratic to have one real root and one non-real root. The reason why is because if you had only one non-real root, for example 2 plus 3i, then you know that the other root is going to be 2 minus 3i. But you can't have three roots to a quadratic equation. A quadratic equation has no more than two different roots. So if you can't have a case where you've got these two roots from the complex conjugate plus another real root. It's just not possible. So these are the only three cases: two distinct real roots, a repeated real root, or a conjugate pair. So let's have a look at example 9 then. So in example 9, we've got a quadratic equation, and we're told that 7 plus 2i, which they called alpha, is one of the roots of the quadratic equation. So in part A, it says state the value of the other root. Well, this is going to be the conjugate pair of A, which is 7 minus 2i, the complex conjugate. For part B, we're asked to find the quadratic equation. Well, we know that we've got these two roots. These two roots are 7 plus 2i and 7 minus 2i, or alpha and beta. Well, because we know the roots of the equation, we know what two of the factors are. We know that z minus alpha and z minus beta are factors. Just as an example, if you knew that a quadratic had roots 2 and minus 3, then you know that you could write the quadratic as z minus 2 and z minus 3. But we just normally write that as z minus 2 and z plus 3. So you know that if you've got roots alpha and beta, then these two have to be factors. So we know therefore that the quadratic equation must have been z minus alpha and z minus beta equals 0. And you can see why these are factors, because if you substitute in z equals alpha, then this bracket's going to go to 0, so you'll get 0. And if you substitute in the root z equals beta, then this bracket will be equal to 0, and it would solve the equation. So now what we can do is we can substitute in what the two roots are. We know that the roots are 7 plus 2i, so I'm going to write that as z minus 7 plus 2i. And notice here that I need to put that in a bracket. And we're going to have z minus 7 minus 2i equals 0. And then now what we can do is we can expand these double brackets. So you're going to have z times z, which is z squared, z times this thing here, which is going to be minus z 7 minus 2i, and then minus this bracket times z, which is going to be minus z times 7 plus 2i, and then minus this bracket times by minus this bracket is going to be plus the two brackets times together equals 0. So now all we've got to do is we've got to try and expand and simplify this quadratic. So we're going to have z squared minus 7z plus 2zi minus 7z minus 2zi, and then expand this double bracket, plus 49 minus 14i plus 14i, and I'm going to do 2 times minus 2, which is minus 4, I times I, which is I squared, equals 0. So now we've just got to try and collect together the terms and see if anything cancels. So straight away I can see that 14i and minus 14i cancel, so I'm going to cross them out. And you can also see you've got 2zi and minus 2zi, and they cancel out. So we're going to have z squared. We've got minus 7z minus another 7z, so minus 14z, plus 49. And then this term here, remember I squared equals minus 1. So we've got minus 4 times minus 1, which is plus 4. And all that's equal to 0. So we recover this quadratic, and we find out that the quadratic is this. In part C, we're asked to find alpha plus beta and alpha beta and to interpret the result. So let's try and work out what alpha beta and alpha plus beta is. So alpha beta is the two roots multiplied together. So 7 plus 2i times by 7 minus 2i. So let's multiply them together. We're going to get 49 minus 14i plus 14i and minus 4i squared, which we can simplify to 49 minus 4 times minus 1, which is plus 4, so we get 53. So you can see that when we times the two roots together, we get 53. And that's because that c in our quadratic is 53. So we know from this little experiment that alpha beta is equal to the constant term in the quadratic, the c part of the quadratic. And actually you can see that from expanding the double bracket, because you see that when we expand this double bracket, the only term which isn't going to involve z is this bracket multiplied by this bracket here. Neither of them have z in them, and that is alpha times by beta. Next, let's look at alpha plus beta. So we need to do 7 plus 2i plus 7 minus 2i. I don't need to write the brackets there, but I'm just showing you that I've got this complex number plus this complex number. So if we add those two things together, we're going to have 7 plus 2i plus 7 and minus 2i, which is 14, because the complex parts cancel each other out. So that's kind of related to b in the quadratic, the coefficient of z. And actually it turns out that alpha plus beta is equal to minus b in the quadratic. And we're assuming that the quadratic's written as z squared plus bz plus c equals 0. So that leads us to another fact that's sometimes quite... If we've got a quadratic, z squared plus bz plus c, with roots alpha and beta, then we know these two facts. We know that alpha plus beta is equal to minus b. If I add together the two roots of the quadratic, you get minus the coefficient of z. And if you multiply together the two roots of the quadratic, you get the constant c. And it's fairly easy to prove that. We know that because alpha and beta are roots, then we know that z minus alpha and z minus beta are factors. So the quadratic must be z minus alpha and z minus beta. So if we times these two together, then you would get z squared minus alpha z minus beta z and plus alpha beta. Well, we can make this look a little bit more like a quadratic by taking z outside of a bracket, and I'm going to write it as minus alpha plus beta z plus alpha beta. Now remember, we're comparing this to the quadratic z squared plus bz plus c. And you can see that if we compare the coefficient of z, these quadratics must be the same as each other. We know that b is going to be equal to minus this bracket here, minus alpha plus beta. So you know that minus alpha plus beta is equal to b. And we normally write that as alpha plus beta equals minus b. So that's our first fact. If you add together the two roots, you get minus the coefficient of z. And also, if we compare the constant term, in this we've got alpha beta, but we know that this is identical to c. So we know that alpha beta equals c. So if you times together the two roots of a quadratic, you get the constant term at the end, c.